Well, hello and welcome to Electricity and Magnetism. This unit is broken up into 4 parts, A through D, and this is the first video for the first part, Unit 5A, Electric Forces and Fields. Our goal in this video is to introduce electrostatics, those physical rules that govern how electric charges behave. Our aim in this video and the next is to bring students to an understanding of the types of charge, the attraction and repulsion of charges, polarization, and how we induce charge by conduction and induction, and to explain how neutral objects can be attracted to charged objects. Now, throughout this unit, whenever we talk about charge, we mean point charge. Just as we used point masses when we learned about Newtonian mechanics, we use the concept of a point charge when learning about electromagnetism. A point charge is simply a positive or negative charge that takes up a single point in space. It lacks any kind of spatial dimensions. So whenever we talk about charges, we're talking about point charges. This is a way to simplify the concept of charge. We're going to begin this video by developing a model of charge that we will be able to use to discuss the behavior of charges, and then we're going to talk about how objects can get charged up by 2 basic processes, conduction and induction. So make sure you've got your notebook ready for note-taking, and off we go. So humans have known about electricity for a long time. Your reading packet goes into a short discussion of the history of electricity if you're interested in such things, but where we're going to begin with here is the knowledge that we all likely have already. Namely, that there are 2 types of charge that we call positive charge and negative charge. There's no real reason we call positive charge, or negative charge. That's just the way it is. But there are predictable ways these charges will behave when they're around one another. Now, there are certain types of materials that can move charge through them. We call these materials conductors, and they're generally metals. Wires are conductors, for example. There's also materials that we call insulators that do not allow charge to move through them, but we can place charge on them through a process we call charging. There are, like plastics, glass, that sort of thing are insulators. For example, here is a plastic rod sitting on what we call a watch glass, and next to that is a glass rod. Both of these are insulators, and what we can see from this triboelectric series is that when we charge up plastics, they tend to charge up negatively. When we charge up glass, it tends to charge up positively. So now we add charge to insulators through frictional forces. Basically, when we rub an insulator with something like a piece of fabric, we pull electrons off of either the fabric or the insulator and add them to the other. So this causes one of the insulators to be charged up with a positive charge and the other to be charged up with a negative charge. The one that gains extra electrons gains a negative charge. The one that gets electrons removed from it gains a positive charge. Now, when you bring charged up objects near one another, they're going to behave in a predictable way. If I have 2 objects that are both charged up positively or both charged up negatively, they're going to repel away from each other. If I have one object that's charged up positively and another negatively, it's going to be attracted. They're going to be attracted to each other. So this tells us that charged objects will exert forces on one another and obey the fundamental law of static electricity. Like charges repel, opposite charges attract. Now you can experience this fundamental law of static electricity very simply with nothing more than a couple of strips of Scotch tape. I'm sure you have some around somewhere, so I want you to actually do this experiment right now. It'll help you understand these concepts we're talking about in this video, and it's actually kind of fun too. So the procedure for this experiment can be found on this website here. You're only going to do experiment number 1 on electrostatics. Basically, you stick a piece of tape to a table, make sure you fold a small section of it over to make a little bit of a handle, and then stick another piece of tape on top of it. it needs to be set up so that the sticky side of one is on the non-sticky side of the other. So press down well and then take them both off the table. Then you quickly pull them apart, holding both pieces of tape. You bring them near each other without touching. You should see them attract toward one another. Next, do it again, but put the sticky sides to each other, and this time you should see them repel away from each other. So this should happen when you put the sticky side to the non-sticky side, and this should happen when you put the two sticky sides of the tape together. So go ahead and pause the video now and give this a try. Okay, so I hope that worked out well. You should have found that one side of the tape charged up positively and the other negatively. You should have also found that when the pieces of tape were closer to each other, they were more strongly attracted or repelled than when they were further apart from each other. The pieces of tape acquired the charge that they had when they were unstuck from each other. The charges on the pieces of tape did not just show up out of nowhere. The charge had to be transferred, had to be put onto the tape from somewhere else. This means that the charges must obey the principle of conservation of charge, namely that charge is not created or destroyed, merely transferred from one system to another. Now, all this information allows us to be able to construct a model of charge that we need to keep in mind throughout this unit. That model of charge can be summarized here. You should pause the video at this time and read through this model and make sure that you understand how it's all been covered in what has been presented so far. Now, diagrams are a useful tool for understanding and explaining charges and the forces between charged objects. This figure here shows how to draw a charge diagram, which gives a schematic picture of the distribution of charge on an object. It's important to realize that the positive and negative signs in the picture do not represent individual charges. At this point, we're thinking of charge only as something that can be acquired by an object by the frictional forces like rubbing. So in the charge diagrams, the positive and negative signs represent the location of the charge only in a general way. If an object is an insulator, such as these glass and plastic rods in the picture, we'll draw the charge just on one section. We do this because charge does not travel through insulators. Instead, it stays where we put it. If the material is a metal, we can show charge being conducted through it because metal is a conductor. Now, when you unstuck the tape, you charged up the tape, and that charging happened as you unstuck the tape. Unsticking the tape involved frictional forces that pulled electrons off of one side of the tape and put them on the other side of the tape. We're going to do several experiments involving charging of plastic and glass rods, as well as some conductive pieces of equipment in class. When we do this, we'll be experimenting with two ways to charge objects: conduction and induction. So charging by induction is really very simple. A charged object, when it's brought into physical contact with a second object, may share some or all of its charges with that second object. So the second object gets the same type of charge as the first object originally had. For example, say we have an object that is neutral. We have a neutral metal sphere sitting on an insulated platform. When we bring an insulated charged aluminum plate to that insulated sphere and touch it, the electrons in that sphere are drawn out of it and into that positively charged up aluminum plate. The result of this is that aluminum plate has less excess positive charge on it, and because electrons left that sphere, it now has a positive charge. Another common way to transfer charge by conduction is through the use of a small metal disc attached to an insulated rod, like this set of pictures here. This device here is called a proof plane. It's used to determine what type of charge exists on some charged up object. So when it's touched to a charged object, it gains the same charge by conduction. The charge can then be transferred to some other object or tested to see what kind of charge it is, positive or negative. So charging by induction is a little bit more involved than charging by conduction. Again, we start out with a charged object and an uncharged object, but this time there is no physical contact between the two objects. There's two ways to do this. We're going to look at the first method first. Here, if I start with a metal sphere mounted on an insulated stand, and then I bring a negatively charged object such as this charged up balloon near it without actually touching, then what that does is it separates the charge in that metal sphere. It causes those negative charges to move to the other side of that metal sphere. Then, if I touch the metal sphere with a finger, it gives those electrons, those negative charges, somewhere to go. It gives them a ground to go to. We call this grounding or earthing. Then, when I remove the finger, leaving positive charge on that sphere, and then that positive charge evenly distributes itself throughout that sphere. The second way of charging by induction involves using two initially uncharged metal spheres on insulated stands. Again, a charged up object, such as this charged up balloon, is brought near one of those two objects, causing those electrons, those negative charges, to move from one sphere all the way to the other side of the second sphere. Then, if I move by grabbing the insulated stand, move the two insulated spheres away from each other, and then remove the charged up balloon, then I end up with a positive charge on the left-hand sphere and a negative charge on the right-hand sphere. Now, a real crucial piece of information, and something that is kind of a drawback of these types of diagrams, is real crucial to remember, is that when objects are charged up, or when charge is conducted through a conductor, they're done so by the movement of electrons only. The positive charges, protons, are not usually charge carriers. So in our diagrams of charged objects, these plus signs indicate that that charge is stationary, it's stuck where it is. A positive charge is obtained from the absence of electrons, not by moving protons around on the materials. So in this diagram here, where it says that the positive charge evenly distributes itself, is a little bit misleading, because that positive charge was already there. It's just that negative charge has been removed. So these diagrams can be a little bit misleading. It kind of looks like these positive charges are moving around. They're not really moving around. The positive charges aren't. Just the negative charge is what moves around. And negative charge will always move to the outside of a conductor. There will be no negative charge on the interior portion of that metal sphere. So this is going to be very important later on as we talk about polarization and the electric field.